So what we're going to do in this video is generalize the notion of induction and recursion to a well-ordered set. So we know how to do induction on the natural numbers, and we also know how to give recursive definitions involving natural numbers. We're going to show that we can extend this to any arbitrary well-ordering. What's the statement that we're going to prove? Let's assume that A less than is a well-ordering. And P of X, some property. Right? Normally for induction, we want to show that some statement is true for every single natural number, say. So we have some property that we want to show is true for every single element in our well-ordered set A. Let's suppose that the following statement is true. So suppose for each y in A, the following holds. So this is going to be our hypothesis. Our hypothesis is that for each y in A, the following holds. Put it in a different color. What we're assuming is that if for each x less than y, P of x holds, then P of y holds. So we are assuming the statement is true for every single y in A. Well, what's the conclusion? Well, then it has to be true that P of y holds for every single element of A. So something I'll maybe mention before we start is that for the natural numbers, I think this might be called maybe something like strong induction, where you're assuming that the statement that you're trying to prove is true for every single natural number less than kind of the natural number you're considering at that time. And that's equivalent to, for the natural numbers, that's the same thing as showing that it's true when n is equal to 0, and then if it's true for n, you show that it's true for n plus 1. So for the natural numbers, that's the same. But for well-ordered sets, that second principle, that weaker induction, just showing that it's only true for successors of elements in your set, that's not going to be the same thing as this statement for well-ordered sets. So showing that if it's true for your least element, and then showing that it's true for your successor, for a general well-ordered set, that's not going to be the same thing as showing that the property is true for every single element of our set A. And maybe I'll try to justify that a little bit more after we're done with our proof. So how does the proof of this thing go? Well, what we want to show is that what do we want to do? Well, let's consider, we want to show that P of y is true for every single y in A. And all we have access to is that this is a well-ordering. So what do we know by that? By definition, we know that every non-empty set has to have a least element. So what we're going to do is, intuitively, what we're going to say is, well, if the property didn't hold for some value if the property didn't hold for some y in A, what would have to happen, because our set is well-ordered, there'd have to be a least element in our set A for which the property doesn't hold. But then it would have to hold for every single thing less than it. But then our following hypothesis would imply a contradiction. Let's write that out. So assume that there is some y such that P of y fails. And what we'll consider is consider the following set. So consider the set S, which is going to be all of the values of A for which P of x fails. That's a set by comprehension. Well, this thing is non-empty. Well, And why is it non-empty? It's non-empty because y is going to be in S. So since A is well ordered, so is a well ordering, S has a least element. And maybe let's call this thing S, little s. As a least element S, little s, in big S. Well, where do we get our contradiction? Since S is an element of A, little s is an element of A, what we know is that the following holds. So by hypothesis, what has to be true? So we know that if for every single x less than s, p of x holds, then it had to be true that p of s was true. So this is the assumption. This is this green statement right here. By hypothesis, S is an element of A, so that statement has to be true. Well, why is this hypothesis of this assumption, why is this true? Well, it's because S is the least element of big S. So what do I mean by that? Since little s is the least element of big S, and what's big S is all the values for which p of x fails. What that has to mean is that for every single x less than little s, p of x has to hold. So we have for each x less than little s, p of x holds. But that's exactly the statement of this hypothesis right here. So what we have is for all x less than little s, p of x is true. This implies that p of s had to hold. This implies p of s holds. And this is a contradiction. So again, if it was false, so if there was a value for which it failed, then there was a least value for which it failed. But by our induction step that we would presumably prove, we'd show that if it was true for everything less than it, then it had to be true for the thing that we cared about. Okay, so let me just I mentioned something before we started the proof of this, that this statement of induction is stronger than the normal induction that you might be thinking of for the natural numbers. And to maybe justify this, let's consider the following scenario. Let's say that we have a bunch of green dots. And let's add so this is a bunch of green dots. We can just think of these as sets, and they're kind of ordered where things that appear first are less than the other things. This goes on forever. And then we have a green dot right at the end. So this is formally an ordinal. It's called omega plus 1, but we don't know anything about that yet. But what is this? This is kind of a copy of omega. And then we have one element that's kind of glued onto the end. And if we wanted to make this more concrete, what we could take is some increasing sequence of real numbers or some increasing sequences of rational numbers, and then include a limit point, include the limit point, and think of that as an ordering that's, and think of it with the natural induced ordering. Well, this is a well-ordered set. So this is a well-ordered set. This is a well-ordered set. And let's say that we want to show that something was true for every single one of these green dots. Well, we can't just show that it's true for the first element. So it can't just be true for this one and then show that if it's true for one, then it's true for the next one. And the reason why is because you wouldn't actually ever prove, if you just showed those two things, you never proved that it was true for this limit point right here. So showing just that p of x is true for the first element and for the successor of an element would not show that the statement is true for every single green dot. How do I want to write this? Would not show p of x holds for the limit point, for the green dot, which is a limit point. Which okay, so maybe I gave it a bit more justification than is required, but for well-ordered sets, this stronger induction is kind of the more natural way, is kind of the correct statement of induction. So what we're going to do next is we're going to prove that we just proved that we can do we can do proofs by induction for well-ordered sets, and what this is going to allow us to show is that we can actually define things recursively on well-ordered sets. So if we have a well-ordered set, we can define some statement, we can give definitions recursively, so where we have access to all the previously defined values of our function. We'll do that next.